Today we would like to refresh your mind about semiconductor and also the simplest circuit device. We call it diode, especially composed of semiconductor. Actually, if you would like to compose that kind of diode, we need two kinds of semiconductors. One is N-type, the other one is P-type, blah, blah, blah. So what is the meaning for that? And what is the important properties you need to know to get a better analog IC design? This is what I would like to help. Anyway, we have quite many elements on Earth. Yeah, we have a lot of elements, and you can see this is the periodic table from the smallest to the largest. And what we are concerned about, how to compose the so-called semiconductor. Actually, we focus on this. All right? Why? I guess simply because the structure is the so-called diamond. Okay, the diamond structure is the most robust, is the maybe also the hardest on Earth. Okay, so we focus on this, and also it has 4 covalent electrons. So it means that each atom will have 4 neighbors to construct the so-called covalent bonds. All right, and but for pure semiconductor, actually, usually it is useless. We need to dope some impurities to make the property even better. Okay, but what kind of impurity? Impurity means what? Not the same, not same atom. That is the so-called impurity. Because for the crystal, usually it is composed of the same atoms. If you would like to dope the others, then they will become impurities. They are not pure. Okay, so we call it impurities to the structure. But who will be the best candidates for the impurities? Again, the neighbors. Yeah, here we call it acceptor. There we call it donor. Yeah. Why we call this? With maybe here the atoms have 3 covalent electrons, and for donors they have 5, right? So 3 less than 4. It means what? You have extra vacancy, the so-called hole, to accept 1 more covalent electron. Okay, so you can accept covalent electron. And how about donors? On the contrary, they have 5, right? 5 covalent electrons, more than 4. But we only need 4. Yeah, so the extra one will be released to be free. So you can donate what? You can donate free electrons. And this is the definition for donors. Anyway, let's focus on the very beginning. Who will be the best candidate? Even for this column. From the beginning, carbon. Okay, is carbon good? For electrical property, yes. Yeah, it can conduct quite much current. Okay, it is conductive, to be honest. But what will go wrong? What will go wrong with carbon? Carbon can be burned easily. Okay, so in the past, humankind, they are not focused on carbon simply because it is too easy to be burned. So we shift to the next silicon. Bingo. Why? Because to my understanding, silicon is the, how can I say, it dominates our Earth's composition. We have more silicon than all the others. Why? The sand, the rock, all of them are composed of silicon. Okay, so we have plenty of silicon to be used. And this is the reason why the best innovation place on earth is called Silicon Valley, right? Because from the very beginning, many of the semiconductor companies, they located in Bay Area of San Francisco. And they are semiconductor companies, so you can guess, every day, every night, they open. Why? In Bay Area, because there are quite many beach, right? So to make the joke, every day, every night, they open the door, yeah, to dig in the sand from the seashore, right? They are all silicon. Then they can make our chips from such kind of beach sand or anything. And this is the reason why Silicon Valley, till now, from the very beginning, I mean, they focus very much on semiconductor business. Till now, that is still the best place for innovation, for money making. All right? And how about the others? Okay, you can go further. Germanium. To be honest, the property will be even better. Why? Because the larger atom, it means what? The core, the nucleus of the atom has less impact on the, how can I say, covalent electrons. It means they can be released even easier, right? So for conduction, germanium is even better than silicon. Why we wouldn't like to use germanium for semiconductor? I guess simply because the price. Either they are much less than silicon, or the process is too poisonous. Okay, so forget about it. That is not for mainstream semiconductor marketing. All right. And then, how about the acceptors? Yeah, actually, boron will be the best. Okay, and for donors, phosphorus. Yeah, later I will have some more comment about this. Okay, has such kind of background from the periodic table. We can go further. From the very beginning, yeah, intrinsic silicon. Intrinsic means pure, okay? Yeah, nothing else, only silicon. All right. So if there are only silicons, what will happen? Oh, they will combine with the neighbors, yeah, to get the so-called covalent bonds, just like this. Why? 2 dash. It means 2 electrons. Okay, to compose the bond. Okay. So, but I have 4 covalent electrons. So my 4 covalent electrons will be shared with my 4 neighbors, right? 1, 1, 1, 1. I share 1 with you. You also share 1 with me, right? So totally, for such kind of bonding structure, crystalline, each body will get 8 totally. The number of covalent, I'm talking about covalent electrons. Totally, the lucky number is 8. And 8 usually is the lucky number for such kind of crystal structure. If you can make the total number 8, it means the structure will be very, very stable. Okay, that's it. According to Bohr model, Bohr model actually was proved already. It is totally incorrect. Okay, according to semiconductor, quantum physics, solid-state physics, actually this is never be correct. But sometimes it's quite, how can I say, it's quite easy to apply to the concept to help us understand the structure of such kind of bond. For example, as I told you, this is the nuclear, right? And to the inside, and the outmost, it has 4 electrons to be shared with its neighbors, and this is the so-called covalent 共价, okay, covalent electrons. Anyway, we have many kind of plots to explain such kind of idea. This is one. Okay, I have 4 bonds, blah blah blah. Also, I have also 4 bonds and 2 electrons in each bond to share with each other, right? But they are not correct. Actually, the 3D model is the best, is the most accurate one, but it's hard to plot, all right? So usually we will be happy with such kind of 2D model, yeah, for easy comprehension. That's it, okay? Again, 2D model is never be correct, but easy to plot, easy to understand, good enough, all right? And this is so-called diamond structure. That is the hardest on Earth. But I mentioned quite many times, incorrect, incorrect, incorrect. All right, what is the correct model? Allow me to show you this. That is from quantum physics. Yeah, actually, don't think, oh, Bohr model is correct. So the atoms, the electrons, just like the moon, circulate around the Earth, right? Is it correct? No, never be correct. Actually, it is very hard to predict the position of the electrons, okay? So according to quantum physics, we can only get the probability of distribution, okay? Where it will show up, oh, it depends on the probability. So you can see, yeah, the brightest one means more probability. That's it. And you can see, wow, the distribution looks very complicated. Okay, that's it. I would like to tell you that actually it is not correct according to Bohr model. It means what? The covalent electrons won't circulate at the exact distance around the nucleus. No, forget about it. Sometimes it will be here, sometimes it will be there, sometimes shorter distance, okay, in any kind of direction. And the distribution look like this, very complicated. You don't need to memorize this. You only need to understand nothing is predictable. No, nothing is predictable. Yeah, it is possible here, here, and there. It is totally possible. Okay, and according to its circulation and self-spin, yeah, such kind of distribution, you can see, is vibrating. Okay, that's it. Very complicated. And then allow me to show you the 3D structure. The 3D structure like this. All right. So in some direction, you will see, wow, very good. Hexagonal structure. Okay, very beautiful. And you can see all the way down, right? In this direction, wow! You can see from the top to the bottom. So what does it mean? If you would like to dope impurities, the other kind of atoms, into such kind of diamond structure, don't inject them in this direction because they will penetrate all the way from the top to the bottom. But this is not what we want. To dope some impurities means what? The impurity atoms need to be embedded. For example, you inject another atom with strong enough energy to kick out one of the original atom. Kick it out, and then you take the position. Stay there. Live happily since after. That is what we call for doping. Tanza. Okay, this is what we want. So don't dope in this direction. Okay, what we need? A little bit tilt. Then it will help the atoms, impurity atoms, to be embedded into the crystal structure. All right. So in last semester, I introduced such kind of doping concept. During fabrication, the wafer cannot lie in this way. No, it will it needs to be a little bit tilted. Okay, that's it. Yeah. Anyway, there is a joke for you. See? What does it look like? What does it look like? Huh? The duckling head. So if your parents, there is a very famous Taiwanese dishes. We call it Dongshan duckling head, Dongshan Yatou, right? So if your parents are selling something like this, you can join us, yeah, for semiconductor business. So many duckling heads. And then the other very important concept I need to mention is such kind of Fermi direct probability statistics, or simply we call it Fermi energy or Fermi level. All right. So what does it mean? For the structure, yeah, even for the incorrect structure, yeah. How about the energy of the outermost atom, electrons? Not exactly the same. Forget about it. Why? Because you can see they are rotating, they are vibrating, and especially according to temperature. Oh, all right. What is the definition of temperature? Oh, kinetic energy of the atoms in the lattice, in the crystal. Okay. So, what is the absolute zero? No kinetic energy. Everybody stay there happily. Don't move. All right? Zero, absolute zero. But if there's any, so how much is 0 degree K? It is minus 273 or something degree Celsius. Okay? Wow, it's really, really cold. So anyway, if there's any temperature, just like right now, about 20 degrees, right? So according to the absolute temperature, wow, about 300. Very hot, very hot. What does it mean? All the atoms in the crystal lattice, they vibrate, yeah, with very much brutal force. They vibrate very much, okay? Some of the atoms, so for such kind of vibration, you can guess, sometimes they collide with each other, and sometimes they collide in the same direction, okay? To collide in the same direction means what? Some of the atoms will be slower down, okay? But to collide with the same direction, it means some will be speed up. So after such kind of vibration, colliding, spinning, anyway, finally, we will have many kind of random process, okay? The energy of myself, of yourself, anyway. This is very hard to make everybody the same. I mean, with the same energy. So according, again, to some kind of quantum physics, blah, 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 it is proved that that is the most correct, most accurate energy distribution for all those, for any kind of electrons, okay, covalent electrons or not, to the outermost or to the inner ones. Anyway, we call it Fermi level, all right? Yeah, it means from the very beginning, again, without any temperature, you will see, everybody stay there, don't move. So every electron has the same energy. But if the temperature is increased according to colliding, right, vibration, blah, 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 the energy will be scared out, okay, spread out. So you can see that from the original 0 degrees to this one, T prime, double prime, triple prime, the temperature becomes higher and higher. What does it mean? Actually, some of the electrons will get more and more and more energy, right? But on the contrary, as I mentioned, the others will lose some energy and lose more, lose even further. That's it. Okay? So this is the equation for you. But you don't need to memorize, no. I would like you only pay attention to this, exponential, okay? All those are exponential curves. Good enough. Keep this in mind, all right? And forget about the equations, because we are IC designers instead of physicians. We don't need to pay attention to such kind of very complicated. Yeah, the equation itself, not so hard, right? Not so complicated. But how to derive it? Forget about it. Quantum physics, solid-state physics. If you are interested, please go to study such kind of very hard physics. Yeah, anyway, we can go further. Yeah, for the categories of the materials, we have different type of solids. Okay, yeah. Anyway, we have insulator, semiconductor, and conductor. That's it. Okay, but what is the major difference? We have conduction band for free electrons, 自由电子. Okay, and for all the others bonding to the atoms, yeah, the outermost we call it valence electrons, valence band. Okay, that is the highest. But anyway, how to make the valence electrons to be free? Well, there is the gap. The energy gap, if it is too large, it means what? It's really, really hard for the electrons here to get large enough energy to be free. That's it. I cannot say no free electrons. No. Again, please go back to this. Unless there is no temperature. Okay, otherwise, never mind what kind of temperature you have, very high or very low. You can see that is the exponential distribution, right? It means what? To infinity and beyond. Never mind how high, how large the energy gap is. Okay, if you go back to here, yeah, for example, this is the so-called insulator, JNT. See? Oh, the energy gap is so high. But you can see, hey, how about the red line? It will expand it all the way again to infinity. Even though the probability above the energy gap is really, really small. But at least there will be some electrons to be free. Okay. But very few means what? Very little current. So we call it insulator. And what is conductor? Conductor. Okay. On the contrary, the conduction band and the valence band, actually, they are fully overlapped. So it means what? By nature, all the valence electrons will be free. Oh, congratulations. That's it. Okay, so for the, especially for metal, for metals, most of them, all of them, I guess, to the definition, they are conductors. So it means what? Congratulations. All the valence electrons will be free, but only for valence electrons here. Okay, how about the inside electron? Oh, no. They are strongly controlled by the nuclear, okay, by the core, so forget about them. But only the outermost ones, they can be free. That is very, very good. Again, according to such kind of distribution, I would still like to point out that some of the valence electrons, they are not free. Okay, because their energy is too low. That's it. Okay? So we have insulator with very, very few free electrons. You cannot say no free electrons. No, that is totally incorrect. But very few. That is for insulator. So on Earth, you don't expect there will be any kind of exact insulator. No, exact insulator means what? No free electrons to carry any kind of current. No, no material like this. But we can reduce the probability, okay, the percentage. That's it for insulator. And conductor, by nature, by definition, all the valence electrons, 价电子, will become free. That's it. But again, not 100% of them. No. Some very little percentage of them will still be bonded to their nucleus. That's it. All right. This is insulator, that is conductor. And in between, we have the so-called semiconductor. That is a very huge money-making business. So for insulator, we need it, but not so much. For conductor, yeah, we need it every day, but too cheap. To make money, you had better focus on this. Semiconductor. Yeah, not so conductive, not so insulative. Very good. That is the definition for semiconductor. But what is the difference? Oh, again, your energy gap is so large, and your energy gap almost zero, right? So in between, semiconductors energy gap is not so high, it's not so low. So again, if you go back here, this is for insulator, and this is for semiconductor. Bingo. With the same temperature, for example, the blue line, right? I will get much more electrons, free electrons than you. That's it. Bingo. I'm more conductive than you, but how about the conductor? Oh, it's here. Almost everybody will become free, right? But some portion will be, not free. Anyway, the conductivity, you can see, conductor much larger than semiconductor, much larger than insulator. That's it. Okay, so I told you much larger. How much? Usually more than 10 orders. Okay, for silicon and metal, yeah. 12 orders in difference. Wow. Really, really much. So according to humankind's thinking, if this is copper, just like the metal wire inside the knife, electrical knife, right? They are very conductive. And this is semiconductor, silicon. Yeah, the tiles, the rock, the stone. According to your definition, the stone is conductive or not? For humankind, no, they are not conductive. Yeah, bingo. That is our intuition. Because for stones, their conductivity is minus 12 order less than metal, than conductor. So for humankind, for our daily life, we don't think it is conductive, right? So again, pure semiconductor usually means useless because the conductivity is really, really bad. Okay, so keep this in mind. Yeah, this is a very important feature. Okay, and then we can go further. According to some reasons, the valence electrons can be free. But how? All right, I mentioned already, temperature, thermal energy. The heater, the higher temperature means what? The more valence electron will be free. But don't forget, the original structure is what? Your parents. Each body has 8 kids. But if one of them becomes free, right? There will be some kind of vacancy. For example, one becomes free, so totally I have only 7. I'm not satisfied because to be stable, I need to gain 8. So there is the vacancy. Vacancy means what? Oh, just like the empty seat. Nobody here, right? So I can invite some outsiders to sit here, okay, and live happily with me since after. Bingo. So what does it mean? The vacancy we call it Hall 电动 okay it's more likely to capture some weak free electron. If there is some kind of free electron very close to me, right, I have a hole, I have vacancy, right, and the free electron is so weak. I mean, the energy is not so much, so I can capture it and put into the hole. Let's say, bingo, I will become 8 again. Yeah, to satisfy myself, because this is the lucky number for atom structure. Okay, for crystalline structure. Okay. So let's come here. Again, according to some reasons, thermal energy is one of them, but not only thermal energy. Okay, kinetic energy the same. For example, you can hit it. The harder you the more, because you just provide some kind of kinetic energy to your crystal structure, right? So many of the valence electrons will be free. Bingo. But anyway, if you don't hit, they will fall back. That's it. All right. So if you that is another joke, right? If your smartphone is too old, too slow, according to kinetic energy, you can hit it to make it, to help it operate faster. Only joking, okay? Don't do it. Anyway, many kind of issues. Not only thermal energy, not only kinetic energy, but also light. Okay? If you shed some light on the structure, some of the electrons will be free. Okay, but energy, for such kind of 3 major energies to make valence electrons free, you need to know that for thermal energy or kinetic energy, only if the energy is larger than energy gap, bingo, the valence electron will be very happy to get some of the portion, because your energy is so large, right? I get this portion, left some for the others. Okay, I just jump up to become free. But how about light? No, for light energy, it needs to be exactly the same. Okay, you say, hey, I shed some light with higher energy. Forget about it. No impact. Only with exactly the same energy, then the light energy will be totally absorbed by the valence electron to be free. That's it. So maybe we call it photons, 光子, will be merged into the valence electron to be free. That's it. Okay? The photons after absorption will disappear, not existed anymore. All right? So exactly the same for light. But you may be curious, how can I make such kind of light with exactly the same energy for the electrons? Really hard. So the usual way is white light, just like our daily light, just like the sunshine. Okay? It has very wide spectrum. Yeah, especially for white light. If you look at the spectrum, the frequency, yeah, you can see it covers from DC, yeah, to very high frequency. Okay, with very flat distribution. That is for white light. Okay, and then because it covers any kind of energy from, I mean, in theory, from 0 to infinity, right? So, at least one will be exactly the same with this. Okay, that's it. But for light, if you go back to here, we have many kind of energy levels, right? So for myself, I need only very small energy. How about this one? Larger. How about that one? Even larger. Okay, so if you expose the white light to such kind of atom, bingo, you will have some kind of, from the spectrum, light spectrum, you will see some kind of black line inside. Okay, for what? You will know what kind of atom it is. That's it. Okay, so in our custom office, if you would like to check some kind of drugs, yeah, you can vaporize the drugs exposed to the light. Then you will have such kind of light spectrum. Then you will say, many kind of drugs. Okay, you will see what kind of drug it is. Yeah. Okay. Again, never mind what kind of energy you have to promote the valence electron to be free, there will be holes here. Okay, empty seat to capture the other electron. So you have free electrons here in conduction band, and in your valence band, you will have free holes. Okay, but I need to tell you, can hole move by itself? Nothing there, just like the empty seat, right? Can this seat move by itself? No, unless in the ghost mouse, okay, ghost month. Otherwise, it doesn't move. But you guys can help it. Just sit here. Then the vacancy seems to move there. That's it. So how to make hole move? I need to tell you, holes means nothing there. It is empty. That is so-called vacancy. Okay? So nothing doesn't move by itself. No. It needs of the others. So the other, especially valence electron, can fill the vacancy here. But if John fill the vacancy for the others, you say, hey, the vacancy moved from here to there, right? That's it. Okay, that is the idea, how holes move. Okay, so the movement in reality of the holes is made by the other electron. Okay, keep this in mind. But that is correct. Anyway, for many of the students, people say, oh, it's really hard to imagine, especially if you read microelectronics, blah, blah, blah. Many of the students, they simply don't get the point. So hopefully, in my class, you will enjoy. According to my explanation, you will get better understanding. Till now, no equation. If there's any equation, I wouldn't like to derive the equation because simply waste your time. Okay? The most important issue is to get correct understanding. That's it. All right? And how about equations derived by yourself if you are interested? Again, I would like to tell you that equations, actually, they are only some kind of help for engineers to understand the operation principles of the circuit, of the device, blah, blah, blah. Okay? So they are minor. They are minors. They are not majors. Okay? They say, hey, I study microelectronics, so the major issue is to derive equations. No. That is really minor issue. According to the equations, hopefully during derivation you will understand, oh, what is the operation principle of the device? That's it. Okay? 他们是配角，不是主角哈，千万不要搞错。Anyway, hopefully that is the analogy. Empty seat in classroom. Yeah, they don't move by itself. Does it work? No. Okay, forget about it. Yeah. Anyway, so from the very beginning, intrinsic silicon, or the so-called pure silicon, okay, they are neutral, charge neutral. That is very important. How the core actually is positive, right? And the electrons, never mind inside or out, to the outermost, all of them are negative. But the positive charges here, okay, the protons, the number of protons, they are positive, right? And the number of electrons, they are exactly the same. So for each atom, it is charge neutral. It is not positive or negative. No, neither positive nor negative. Keep this in mind. All right? So in this way, if according to some reasons, kinetic energy, thermal energy, light energy, okay. Anyway, some of the covalent electrons becomes free, but free electrons means what? Negative, right? Right? So the holes are forced to be positive because from the very beginning, this is neutral, right? So after some promotion, the valence electrons becomes free to be negative, but the overall charges will be exactly the same. So yeah, if you have 3 electrons, they are negative, then it means 3 holes needs to be positive to cancel each other, to balance the charges. But to be honest, if you ask me why the empty seat is positive, it doesn't make any sense, right? Because nothing there. It cannot be neither positive nor negative. Actually, again, if we go back here, yeah, totally we have 14 protons here, okay? And overall 14 electrons, 10 inside and 4 to the outermost. They are just neutral. But one of it go away. So totally, we have positive 14 and negative 13, right? So totally, the overall charges becomes positive. So we put the blame on the empty set. Okay, you are positive. Actually, not the hole is positive. Actually, is the nuclear. Okay, but to get better understanding, okay, for easy explanation, usually we just force the empty seat to be positive. That's it. Congratulations. That's it. Okay. Again, that is the easiest way for professors to convince the students, the holes are positive. But in theory, that is totally incorrect. Nothing there. It couldn't be positive. Okay. So we put the blame, 1 extra proton. We think, we guess, okay? The positive charge here is, we just shift the so-called charge to the hole, okay? The extra positive charge. Okay, anyway, so again, in this way, it will be easier for the students to keep this in mind. They are charge neutral because you have 3 electrons, you have also 3 positive holes, so positive 3, negative 3, totally charge neutral. Okay, easier to get not so correct understanding. Okay, the outcome, the result is correct, but the explanation is totally incorrect because hole is nothing. Okay, hole vacancy, nothing there. How can it be positive? No way. But okay, forget about it. Yeah. You just pretend holes are positive, okay, to make your life easier. All right? And then we go further. According to thermal energy, some of the free valence electron will become free. We call it thermal generation. For such kind of thermal generation, you will see the total number of free electrons will exactly the same as the total number of free holes. Okay? Got it? How many electrons to be free? There will be how many holes for the crystal structure. That's it. So they are the same. And again, congratulations. This is negative, that is positive. Oh, yeah, let's pretend they are positive. Then you will keep, again, charge neutral. Congratulations. Okay? But not only thermal generation, you can have kinetic simulation, light generation, all the same. Never mind in which way. The total number of the free electrons and free holes will be exactly the same. Okay? And then, in this way, you will say, hey, we have only if there is temperature. I don't care here, here, over there. Only if there is temperature, you can see the energy gap here. That's the energy, okay, from 0 to infinity. But never mind how much temperature it is. There is some percentage here, or for this one there, right? For this one there, yeah. There are always some some valence electrons get enough energy. I mean more than Eg, energy gap, to be free, right? So you say, hey, gradually all the valence electrons will become free. Okay? If there is only one mechanism for thermal generation, yeah, I promise you, sooner or later, all the electrons here will be free, but it doesn't make any sense. So it means what? You put the semiconductor here, then wait for a longer time. Wow, bingo, it will become more conductive? No, no. Never, right? You put a rock, a stone here, wait for 1 year, it will become conductor. Forget about it. Totally impossible. So it means what? There is one mechanism. It should be the other reverse mechanism. That's it, to balance it. So it means what? You can generate new free electron and hole, right? The other mechanism will pull it back. Bingo, that's it. That is the so-called recombination. Again, for the holes, here, it is always desired. It always desired to some kind of weak electrons, free electrons, yeah, to make the total number back to 8, like the lucky number. That's it. Okay, so the you can guess the hole is always watching. Oh, okay, some weak electron just flies through. I capture it. Bingo. If you capture the weak free electrons to fit into the hole, right? Then you kill one free electron, also one hole. So anyway, never mind for generation. We generate in pairs. What do I mean? One electron, one hole. Okay? And how about the recombination? The same. You kill in pairs, again, to kill one free electron, weak free electron with one hole. That's it. So again, I would like to remind you, under such kind of circumstances, for pure semiconductor, the total number of free electrons and free holes should be exactly the same. Okay? Never mind how hard you generate it. The more you say, hey, if I increase the temperature, see, from this one to that one, wow, a lot of the electrons will become free, right? Bingo, yes. But the more free electrons here, it means the more holes here, it will be easier for the holes to capture free electrons, right? So the more electrons to the sky, it means the recombination rate will be also increased. Finally, you will get another balance. That's it. Okay? See? So you cannot simply, oh, this is the stone. I heat it up. Finally, it will become conductive. Forget about it. Okay? Yeah, the total number to be free will be increased. But again, it won't just like I say, right? Not all of them will become free because the reverse mechanism will balance the whole process. Okay, that's it. Yeah, anyhow. So this is intrinsic silicon, pure silicon. Wow. After some kind of semiconductor, blah, 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 quantum physics, solid state physics, oh, you will have N equals P equals Ni. I means what? The number of intrinsic semiconductor. Okay? Yeah. it looks like this. Oh, don't ask me how to derive it. I'm your professor for IC design instead of quantum physics. Okay, according to quantum physics, solid state physics, you will know how to derive it, but not my business. Okay, I would like to tell you only that they are strongly dependent on temperature. Okay, good enough. But again, if you go back to this, you will know, you will know. Yes, yes. The higher temperature, the more free electrons will be generated. That's it. Okay? And we can go further. Since right now you have more electrons, more holes to move, right? So the semiconductor will help you to conduct some of the current. But according to current conduction, we have, again, two kinds of mechanisms. One is diffusion. The other one is drift. Okay? So what is diffusion? What is drift? All right, allow me to explain. Diffusion means what? For example, you have a cup of water, pure water, right? And then you have some kind of red ink or black ink. Just put in one drop and watch. Wow! The ink will spread all over the water. Sooner or later, it will become, how can I say, homogeneously black or homogeneously red. Okay? So that is the definition for diffusion. Okay, that is the cup, water, or you put some kind of sugar or salt. Gradually, they will diffuse from here to there. Okay, so what is the operation mechanism of diffusion? From high concentration to low concentration. That's it. Okay, so we can see, hey, for example, this is for hole, that is for electron. Okay, but they look all the same except for the minus sign. That's it. Okay, let's focus on hole first. For hole diffusion, for example, this is the concentration profile, the distribution of the concentration. As I told you, the tendency is from higher concentration to lower concentration. That's it. Okay, so it means what? The difference, the slope. The higher slope means what? More potential to move to the other direction. Okay? If it is flat, the concentration exactly the same. So it means what? The slope is zero, right? No motivation. Because here, there, and there are the same. I wouldn't like to move to any place because all of them, right? But again, just like the water, this is higher, that is lower. So the more slope, right? It means the water will flow even stronger from the high to low position. That's it. All right. So the tendency of such kind of diffusion depends on the density difference. Okay. So differentially, it will become differentiate. Even. Okay. And then, but I can only say, hey, the higher slope, the more diffusion. So it means what? The diffusion is proportional to the slope. That's it. So what does it mean? Y proportional to x. It means what? Y equals a by x, right? Some kind of proportional constant. Bingo. So the proportional constant for whole diffusion, we call it dP. D means diffusion. P means what? Whole, positive. Okay? So that is whole diffusivity. Okay? And then for whole, because it carries one positive charge. Okay, the charge in magnitude is equal to electrons. Okay, so the Q means what? Hall charge, and this is the same Q, right? Electron charge. The only difference, one is positive, the other one is negative. Okay, that's it. But again, you can see the slope here is negative, right? But the hole will diffuse to the right, positive. Okay? So it means what? There is, so for example, another example, look like, oh, the slope is positive, but the hole will diffuse to the reverse direction. If I'm positive, you are negative. I mean the move direction. If I'm negative, then the move direction is positive. So there is one minus sign between those two. So we got positive here. That's it. Okay, got it? That's it. And how about the diffusion of electron? Exactly the same. The only difference is the diffusivity for electrons and the diffusivity for holes are not the same. Again, electrons can do it by itself. And how about holes? Can the empty seat diffuse by itself, move to the other? No. Okay? Only, oh, the density over there is, yeah, the student seat over there is too crowded, especially in under hot weather. Okay, if the temperature inside is really hot, then the student there will say, oh, this is too hot. Some of the students will diffuse to take the other empty seat to get cooler, right? So under such situation, especially if the temperature inside is really hot, I don't think the students will gather to the back side. You will scatter to take the empty seat. Okay, that is the definition for Hall diffusivity. So holes again wait for the other electrons to take their position. So it is harder because you cannot move by yourself. You need to wait and see, right? But for free electrons, they can move freely. They are free. They are totally free. So the diffusivity of electrons is much higher than Hall. So how much higher? Almost 3 times higher. Okay? Yeah, a little bit less than 3. So usually we will say 2.5 to 3. Okay? Around 2.5 higher or 3 times higher. That's it. Diffusion. Yeah. So for diffusion current, you will see for the same concentration, wow, the holes will diffuse to the right. And how about the current? Because it is positive, so the current will also flow to the right. Okay, the direction of your current, diffusion current. How about electron? The same profile. The electron will diffuse to the right, but the electrons are negative. So the current flow, the equivalent current flow actually is to the left instead of to the right. Okay? With the same profile here, with the same profile there, here for holes, here, there for electrons, you will see not only the direction of the current flow are not the same, but also the magnitude. Why? You are larger, I am smaller. Simply because this dP is almost 3 times lower than dN. That's it. Okay? Got it? Then we go for the drift. All right. How to drift? Yeah, in this way, you just think about electron. For free electron, if you this is your semiconductor, your any kind of conductor, resistor. Yeah, positive here, negative there. So for all free electrons, by nature, they will be attracted by the positive potential, right? Right? So all the free electrons will move in that direction. I mean to the right. Is it correct? On average, yes. How can I say? For macroscopic view, 巨观, correct. All the free electrons will move from the left to the right, from the negative to the positive, exactly. But for microscopic view? No. Why? Because, again, only if there is any kind of temperature, the crystal is vibrating, right? So the free electron would like to flow to the right, but the atom is vibrating, so the electron will be collided with the atom. The microscopic view of each free electron, it won't go this way. No. Okay, even positive here, negative there, it will go here. Then, according to collision with the crystal, okay, bang, dang, 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 dang. That is the so-called drift. Okay, that's it. It won't go smoothly all the way from left to the right. No, 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 no. During the process, it will be scattered. But gradually, it will move from the left to the right. Yes, on average, correct. Okay, that's it. That is the definition for drift. And how about holes? The same. Yeah. Again, it needs another electrons to fill the empty seat for the hole. Okay, so you can see for electrons, electron velocity, yeah, it is directly proportional to electrical field, 电场. The larger E means the larger V. Bingo. But again, I am proportional to you. It means you need the other kind of proportional constant. Bingo. That is this is even more important than the previous one. Mu n means what? The mobility. Mobility here. The mobility of negative electron. Similarly, we have Hall velocity. Yeah, the speed for holes. Yeah, proportional to electrical field, and the proportional constant is mu p, mobility for holes. Okay, got it, right? For semiconductor engineers, mobility and mobility p are very important parameters for you. And again, you can see, wow, this is for mu p, that is for mu n. If you divided this by that, again, almost 3 times. Wow, what a consequence. Coincidence. Okay? What a coincidence. If you divide this by that, or you divide this by that, I promise you, you will get the same number. Wow, bingo. Never mind for mobility or for diffusivity. Okay? The electrons get better mobility than holes with exactly the same times. Okay? Yeah. So I would like to tell you this. This one. Albert Einstein is not only very good at atomic bomb, okay, but also it contributes a lot to our physics. Oh, really smart guy. See? This is a very famous one in semiconductor field. Einstein relationship. Yeah, blah, 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 blah. It means what? Again, diffusivity of Hall over diffusivity of N exactly equal to mu p by mu n. Exactly the same. Okay? Yeah. How better I am over you, exactly the same as how much better in mobility I am over you. That's it. Okay? Yeah, so you need to worship Einstein. Oh, he's really, really smart. Okay, let's go back to finish for such kind of drift. Current. All right? So overall, in any kind of conductor, semiconductor, blah, 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 you have free electrons and also holes. Both of them will help you to carry the current. Okay, so for example, there is a semiconductor, positive here, negative there. So electrons will move to the right. Holes will move to the left, right? How about the total current? They don't cancel each other, right? No. Because again, the electrons is negative. So to the right means what? The total current will to the left. So they help each other instead of cancel each other. No worry. So the total drift current is the summation of the holes and the electrons. All right? Yeah. And here, from here and there, two more parameters for you. P means what? The density of holes. And N means the density of electrons. Okay? The higher density means the more current you can carry. Oh, that's it. Very easy to understand. Okay? Density in which way? Oh, how many holes or electrons over unit volume. 单位体积里面有多少个电子或电动 ？That's it. Okay. Bingo. So you can see, if it is constant, I mean, for a resistor, how many? What is the concentration for your holes, for your electrons? Yeah. Under the same condition, I mean, for example, at room temperature, blah, blah, blah. Okay, you can see, density fixed, mobility fixed already, right? And you apply the fixed electrical field configurations, the drift current will be fixed, okay? But anyway, the drift current will be proportional to the electrical field. If you, enlarge the field, you will get more current, okay? You get this one. So totally, we sum up, if they are fixed, all those, okay, except for E, then this is some kind of proportional constant. The current density is proportional to the electrical field, and the proportional constant, we call it conductivity. And this is the base for what? Ohm's law. That's it. Just do it by yourself. Very easy, okay? Current density means what? The total current by cross-sectional area. That is the definition for current density. And what is E? You apply voltage, and this is the length, okay? Voltage by length become electrical field. That's it. So after this, you get that. Congratulations. This is Ohm's law, okay? Yeah. So the resistance proportional to the length and reversely proportional to the cross-section area. That's it. Okay? Very, very easy. You learned it already from your fundamental physics. Right? So before the break, I would like to tell you how holes can move. Okay? Yeah. With a more correct, more accurate explanation. Again, the empty seat cannot move by itself, but how the others can help. All right. For example, this is the intrinsic silicon lattice finger without applying any kind of voltage, electrical field. All right. So they look like this two-dimensional model. Not so accurate, but easy to understand. So for the hole, for example, the hole here. Why? There is a hole. Because according to thermal generation, the valence electron here go away. So it leaves a vacancy, a hole here, right? But who will fill the hole? To be honest, your brothers. This one. You say, oh, there is empty seat. So it goes here. But later you say, oh, the empty seat there, right? So to be honest, the hole will oscillate. Yeah, in this in this bond, okay, here or there, here or there. But anyway, by some chance, you will see when the hole is here and the neighbor valence electrons, again, I show you this. According to probability, don't expect those two will be bounded. No. Inside the bond, no. According to the probability, sometimes it will show up here. Sometimes it will show up there. Sometimes it will show up here, right? Bingo. If the electron, according to such kind of probability distribution, sometimes it will go much closer to the hole. Okay, congratulations. You will say, hey, there is an empty seat. I would like to sit here. Congratulations. What will happen? This one will fit the empty seat here and leave the hole there, right? Right? So it means, to your own views, you say, hey, look, the hole is shifted to there. But actually, the hole, again, itself cannot move. Only because the electron here to fill its vacancy. So it looks like it moved to the other side. That's it. But if you ask me, hey, why you guys here fill the vacancy? Why not that one? Yeah, the same. According to probability, the vacancy may be filled by this one or by that one with exactly the same probability. Okay? And also that, as I told you, the easiest way to fill the hole is by the other electron here. Yeah, your roommate. They are neighbors, but you are roommates, so it is more likely to be filled by your roommate. In that way, the hole will be here, right? So again, the probability to be filled by this or by that, exactly the same. So on average, for such kind of hole, move to the top, move up, move down, move left, move right, move left, exactly the same. So on average, no movement. I mean, for macroscopic view, the electrons, the holes, they don't move. But for microscopic view, oh yeah, filled by this, filled by that, blah 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 blah, randomly move, right? Yeah. So on average, for nothing, they moved very quickly, but for nothing, because on average, the movement is not to the right, not to the left, not to the top, not to the bottom. No. On average, 0. That's it. Okay. So if you look them far away, you say, hey, no movement. But if you zoom in and zoom, wow, everybody is so busy. Not only for the free electrons, but also for the holes. They are very busy, but for nothing. Okay? Then, if you would like them to do something for you, not for nothing, okay, let's apply some kind of electrical field. For example, oh, sorry for that. I make wrong modification. Yeah, if you apply some negative field here, positive field there, it means what? All the free electrons, sorry, all the valence electrons, they will be attracted by the positive potential and pushed by the negative potential. So what does it mean? The distribution will be distorted. Okay? From the original one, then move a little bit to the right. Got it? Because to the right, positive, I like it because all of us are negative electrons, never mind free or valent. Okay? So, just for your reference, the black dust means the original state. Okay? And The red one means attracted by the positive, sorry, positive here, negative there. Shift it a little bit to the right. So what does it mean? Under such kind of situation, you will guess more likely, right? If the Hall is here, right? According to the distribution, sorry, it's incorrect, okay? The electrons, valence electrons, are pushed a little bit to the right. So it means what? The Hall is closer to here than there, right? So more likely, the left valence electron fill the vacancy. Bingo, bingo. So it means what? On average, the Hall will move to the left. See? That's it. If you ask me, how about the top or the bottom? The same. You can see, right? The distance to the top, to the bottom, to the top, to the bottom, the same. So the probability according to positive here, negative there, they will only flow to the negative. I mean the Hall will be filled, then move to the negative. Okay, that's it. That is how Hall can propagate through silicon lattice, filled by the other valence electrons. Okay? Yeah, so that is the current summary for you. All right, we can have a break right now. Till now, I am all talking about pure semiconductor, intrinsic semiconductor. It takes more than 1 hour, right? But for what? For nothing. Why? Because pure semiconductor means useless, always, usually. Okay? If you would like to make your semiconductor, more useful, to get better function, you need to do doping. Okay? Yeah. You need 掺打几边那下 Okay, 掺打 Alright. You need to doping. To dope impurity. Again, what is impurity? Impurity means the other kind of atoms. Okay, different from the original one. Very good. After doping, you will get much better performance than the intrinsic one. Okay, this is also a very good lesson for humankind. On the contrary to Donald Trump, he always thinks, oh, the whiter the better. Oh, no. Intrinsic white guys, usually the performance is no good. If you go to Silicon Valley, you will see a lot of Chinese, Indonesians, many kind of Asian guys, okay, Indians, Filipinos. If you go to in last semester I went to Silicon Valley for a short visit. I visit Apple, Facebook, Google, all the way. Looking inside, wow, all colorful people. The percentage of white guys really low. Okay? Okay? So, purity is no good. Impurity is much better. Okay? That is maybe the reason why Donald Trump had better take my lesson. Wow! He will become a much better president than before. All right? But the other sad story is, even though the white guys in such kind of international, huge international companies, the percentage is really low. But most of them are managers. Okay? Because that is their country, not ours. Sadly enough, even though your performance is better than theirs, even though you stay there for a long time, or your kids, your grandkids, they behave just like native American, right? They can speak English without any kind of accent, but according to your, appearance, you say, oh, you are good. You are very smart for engineers, but you are not very good at management. Is it true? No. Yeah. Anyway. So, had better all those politicians, they learn something from that kind of doping. Hybrid, okay? Hybrid is usually the best. Okay, let's have a break right now.